Yesterday, we started talking about how objects acquire an electrical charge, and we talked about what I think, as far as the Regents is concerned, at least, the most important way that objects acquire an electrical charge, and that was conduction. I mentioned yesterday, though, very briefly before we started talking about conduction, that there are two main methods by which an object acquires an electrical charge, and those are conduction, which we started and finished yesterday, really, and the other is induction. Now, today we're going to talk about induction. So, the first thing to say is that this topic can get a little more complicated than is required for us to discuss on the Regents. And it will seem like we are not going to talk about this in like a huge amount of detail today. That may be true, but essentially what I want to do today is just cover the basics. Now, as you've probably noticed so far this year, a lot of what we do at one time of the year ends up coming back again later on, and you will see that with conduction and induction when we get to another topic. And so today we want to just cover the basic details, just sort of lay the groundwork for you to start to be able to conceptualize this, and then next week you'll see that there'll be more opportunity for you to put it into practice. So at this point, it's probably smart for us to just jump right into it and get into the topic of induction. All right, so the first thing that we have to ask here really is, what is induction? And induction occurs when a charged object is brought near another object. Notice there is no touching involved in this process. Honestly, I think you should write that next to this definition, wherever you're writing this definition, hopefully in your books. Induction occurs when a charged object is brought near another object, but does not necessarily touch it. All right, so I went ahead and added it in there. So we're saying induction occurs when a charged object is brought near another object. It could have a charge, but it might not. But it does not necessarily touch it. Now, there's a very important note that we have to make, which we will go ahead and make later. But the important thing to realize here is that because the objects are not touching, there is actually no transfer of charge. So yesterday we were talking about conduction. We said when objects come into contact, due to the attraction and repulsion of electrically charged particles, the objects will, or I should say specifically the electrons will move around such that they balance and you'll have an equal final charge on each object. That's how conduction works. Because the objects are touching, there is charge transferred. However, in induction, because the objects are not touching, there is no charge transferred. So now the obvious question to ask here is, well, if there is no charge transferred, A, what actually happens? And B, why are we even talking about this then? Well, because it's more interesting than it looks. Obviously, the question here is, how would introducing a charged object near some other object, we'll just call it a test object, affect the test object? And the main idea here is that just because the objects are not touching doesn't mean nothing's happening. Because, for example, even when you're like diving off a diving board and you're in midair, just because you're touching the earth, or just because you're not touching the earth, doesn't mean the earth is not exerting a force on you. Gravity, like the force of electricity, is a non-contact force, meaning it still acts when the objects are not actually touching. And so the basic idea here, and this is a super important point, is that when a charged object is brought near another object, like this test object we're talking about, the charges inside the test object redistribute themselves. That's a key detail. And if you're not quite sure what I mean by that, I'm not surprised by that at all. We're going to have to go through a couple of examples. But first, We just have to clarify one brief little point before we get to it.
Before we do that, I'd like you to write this down. So take a second to pause this video here and write that down. When you hit play, move on.
Now, before we move on, we just have to ask one quick little clarifying question to clear up what is going to prove itself to be a very important point in this unit. Now, let me just take a second to say, some of you will find this question to be a waste of time, because the answer to this question will be so obvious to you that you might not pay attention to all the subtle details. Let's be clear, this is more complicated than it seems. So whether you think you know the answer or whether you really don't know the answer, it would be very important for everybody to pay attention to this part. The big question that we have to ask here to clarify what will prove itself to be a very important point is about the difference between a neutron and a neutral object. And so that's the question. What is the difference between a neutron and a neutral object? I think it'll probably make a decent amount of sense I think it makes a decent amount of sense to talk about the similarity between a neutral object and a neutron, because that will make it, I think, perhaps a little easier to understand the differences between them. So let's ask another question first. The other question is, well, what is the similarity between a neutron and a neutral object? Well, a neutron has no charge, and a neutral object has no charge. But as far as we're concerned for this course, a neutron and a neutral object have no charge for different reasons. And that ultimately is the difference between a neutron and a neutral object. So the key point here is, since a neutron is just a single entity, it is a particle that just has no charge, a neutron is just a single particle with no charge. That's it. However, a neutral object has many, 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 many positive charges and many, 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 many negative charges. And so while a neutron just has no charge, a neutral object is made up of a ton of charged particles, positive and negative. But the idea is what makes that object neutral is that there are equal numbers of positive and negative particles. And so the positively charged particles all have a positive charge, which you would add up all the individual charges to get the total positive charge. And the negative particles have a negative charge, which if you added all those charges up, you would get the total negative charge. And the idea is, because protons and electrons have the exact same size electric charge, but they just have the opposite sign, if there are equal numbers of protons and electrons, the total charge effectively cancels out. The positive charge cancels out the negative charge, and so there's zero total charge. Now, this ultimately is important because this difference, the fact that a neutron just has no charge, but a neutral object has positive and negative charges that just happen to cancel out, means they behave in fundamentally different ways. As we'll see tomorrow, when we start to talk about forces, only charged particles feel forces, electrical forces at least. And so because a neutron is not a charged particle, it does not feel an electrical force. So the big question is, because a neutral object is neutral, does that mean it experiences no electrical force? Or does it experience an electrical force because it is made up of positive and negative particles? Obviously, there's only one way to find out.
And that would be by doing a little experiment. Before we do that, though, I'd like you to pause this video here and write that down. And when you hit play, we'll move on.
This is a clump of paper, cut up. Just regular printer paper. Cut it up with the scissor. Scissors right here if you don't buy it. Okay. This is a comb, just like a regular old comb. It's actually super long. I found it at a dollar store. It also is neutral. And so what's going to happen when I bring the comb close to the paper shouldn't be much of a surprise. Yeah, nothing happens. That's because neither of these objects have a charge. But if you've ever tried to stick a balloon to a wall, then you probably know how I can give this comb an electrical charge. I can give the comb an electrical charge by rubbing it on my head. Now, I'm going to show you a slide about this in a second, but the reason why rubbing something on your head gives a charge to the thing you're rubbing on your head is because your hair is basically just like a big electron warehouse. It has a ton of electrons, which are super easy to remove from your hair. And so that little bit of friction provides enough energy, kind of like in the video I showed you yesterday when I was rubbing my socks on the carpet. The friction between the balloon and my head or the comb in my head is enough to, well, it's enough to rip away the electrons and have them stick to the comb. So I'm going to take this comb and I'm going to rub it on my head because I thought I could flip the camera around in the middle of this. I was going to show you show me rubbing the comb on my head, but I guess, you know, nobody needs to see that. But hopefully you'll be able to hear it. And I want you to listen very closely. If you have headphones, maybe you want to put them on because it is fairly cold today, although the heat is cranking in my apartment, as maybe you heard in the background. And because it's cold, we might actually be able to hear some of the charge leaking off of the comb, and you'll hear like a little spark or a little static shock as I'm rubbing the comb on my head. And I'm going to do this very close to the speaker, so maybe you'll be able to hear it. Okay, I'm not hearing that popping because apparently it is a little humid today. And so it's not quite working, but I am rubbing this comb all over my head, getting it nice and charged. And now the comb has a charge. Watch what happens when I bring it close to the paper. Ooh. Let's try that again. Maybe with the thick side. Oh yeah, now we're getting some attraction. Now this is confusing because the paper was neutral. I mean, the comb was neutral, but I rubbed it on my head, so I gave it a charge, but the paper is still neutral. And even though the paper is neutral, it still is attracted to the comb when I put the comb near the paper, and it gets stuck to it. And notice it's pretty strong force of attraction because it just took a while for that piece to shake off. There's also another good example of this that I'd like to show you, which, if I can get it to work, will hopefully appear in a second. Okay, so all of you will have the opportunity to try this at home because I'm assuming all of you have a sink. Obviously you do. And if you have a comb or even a balloon, this will work. However, it will only work in a sink that is capable of providing a super thin stream of water. So if you turn it on like this, it's not going to work. You got to really just let the water trickle out in as thin of a stream as possible without breaking up like it kind of is now. So really more like that. And so I'm going to rub the comb on my head. I want you to watch what happens to the water. Even though the water is neutral, it's still attracted to the comb. And instead of falling straight down like gravity wants it to, it's attracted to the comb. So this brings us to a key point here. Neutral objects can be attracted electrically. Notice I bold, underlined, and italicized the word objects. This does not apply to neutrons. Neutral objects can be attracted electrically because they can experience a temporary charge distribution caused by induction. And this distribution of charge will allow them to experience a strong enough attraction between opposite charges. Now, that's confusing. Let's be clear about that. But I think it'll be easier to understand once I draw this diagram. So take a second to pause this video here and write that down. When you hit play, we'll move on. So, as I mentioned, the phenomenon of a neutral object being attracted electrically is kind of confusing. I really wanted to take a moment at this point in the video to spend some time drawing a diagram and really going over this in great detail because I think it'll make it a lot easier for you to understand. It's important to recognize
that we are saying here in this particular instance that when we temporarily charge something by induction, we are allowing the object to have a temporary distribution of the charges. Essentially, what's happening is the charges are going to rearrange themselves. And so let's go ahead and look at how that's going to work. And for this first example that we're going to use here, we're going to use the example of a negative charging instrument, an object that's coming in that's negatively charged that's used to attract a neutral object. And we'll use the basic example of a comb being able to attract a piece of paper, since that's the example that we already talked about here at this point in the video. And so what we're going to do is we're going to draw like a before and after diagram. So here is the comb. Let's just say this is a comb that's obviously pretty awfully drawn. And this comb is negatively charged, as is shown by the negative charges that are on the comb. And we had the paper over here being attracted by the comb. And this piece of paper was like ripped and cut up, so I'm just going to draw a squiggly little chunk of paper. And remember, we said this paper is originally neutral. The way in physics that we usually represent objects that are neutral is we just draw a series of like plus minus signs like this. The reason why we do that is because we don't want to randomly scatter the pluses and minuses throughout the diagram, because we don't want to put anybody in a situation where they have to like count up the pluses and count up the minuses and see if there's the same number. If you look at that and you see for every plus there's a minus, then you know this thing is neutral. So the piece of paper is originally neutral. Now, of course, the whole point of this is to really answer the question, well, what happens after we move the comb close to this piece of paper? So now instead of this thing being all the way over here, far away from the paper, we take the comb and we move it right up close to the piece of paper. Notice the separation distance between the comb and the paper. They are not touching. If they were touching, that would be an example of conduction. This is not an example of conduction. It's an example of induction. This thing is, as we say, inducing a charge distribution in the paper. So the question that we have to ask here is what's going to happen to the positive charges that were in the paper, and what's going to happen to the negative charges that were in the paper. Let's start with the positive charges. What's going to happen to the positive charges? Well, the answer here is pretty obvious. The comb is negatively charged. And so positive charges are usually attracted to negative charges. And so that means they're going to be attracted to the negative charges on the comb, right? No, that is not the case. Remember, protons do not move in solids. Notice how I just said when we were going through this, we're going to start with the positive charges. Never do that. Always start with the negative charges. Those are the only ones that are going to move. The protons don't move in the solid piece of paper. So when we ask ourselves the question, what's going to happen to the electrons that are inside of the piece of paper, it's a question that's equally as obvious. The comb has negatively charged electrons on its surface. It picked up the negatively charged electrons from my hair when I rubbed the comb on my hair. As a result, the electrons in the piece of paper are going to be repelled by the electrons on the comb. That means they are going to move over to the right-hand side of the piece of paper. Now, I'm going to fill in the rest of the diagram so we can talk about what this is going to look like. Notice here, whenever I talked about this, I said the piece of paper is going to experience a temporary charge distribution. What I meant by that is essentially one part of the paper is going to be behaving as though it has one charge, and the other side of the paper is going to be behaving if it has another charge. Now, that's not totally accurate, but it's more or less correct. Let me tell you what I mean. It is true that electrons are repelled by electrons. So the electrons in the paper are going to be repelled by the electrons in the comb. But it's not like they're going to be able to bunch up all on the very end of the paper farthest away from the comb. Why not? Well, because while the electrons are repelled by the electrons in the comb, these electrons are also repelled by each other. So they bunch up as far as they can get over on one side of the paper, but they don't totally go over to one spot. They're sort of distributed throughout the right-hand side. It's important to realize these diagrams are a little misleading because it would be impossible for these diagrams to account for all of the charges in this piece of paper. There are literally trillions of protons and trillions of electrons in this piece of paper. There are still protons on the right-hand side of this piece of paper because, as we said, protons don't move in solids. But the point is, now, because there are way more electrons than protons on the right-hand side of the paper, we draw only negative signs just to show the electrons are clearly outnumbering the protons. And so the net charge on this side of the paper is negative. That's the point. Now, as far as the left side is concerned, it is true that not all of the electrons were able to make it over exactly to this one half of the piece of paper. But it is clear that on this side of the piece of paper, the protons, which never ended up moving in the first place, because again, protons do not move in solids, they are now clearly outnumbering the electrons on this side of the paper. That's why we represent this side as being a net positive charge. So it's important to realize in these scenarios, the protons are always going to get left behind, and the electrons are always going to move in such a way that is always described by the principle that opposite charges attract and like charges repel. The electrons are repelled, so they move over to the right side. The right side now has some protons, but way more electrons than protons, so the right side has a net negative charge. The protons on the left side never moved in the first place, but the electrons left. And so this side has a net positive charge. I actually want to write down some notes about this. So take a second to pause this video here and copy this diagram down. And when you hit play, we'll move on. Okay, so the first note about this that we can write here for charging a neutral object is that the protons don't move to the left. That's not why the left side is positively charged. They're left behind by the electrons that move to the right. This means that on the left side, there are many more protons than electrons, so it has a net positive charge. Obviously, as I mentioned, the same can be said about the right side, how, yeah, there are still protons over there, but there are more electrons than protons, and that's why we say the right side has a net negative charge. Now, of course, we can ask the question, yeah, the protons are left behind, but why are the protons left behind? Why don't they move left? Remember, protons do not move in solids. That is a critical point to understanding all of this stuff. Take a second to pause this video here and write that down. And when you hit play, we'll move on.
So just to make it perfectly clear, this is also how a balloon sticks to a wall. It should be pretty obvious to everybody that a wall doesn't have an electrical charge. Like all other atoms in their natural state, a wall is neutral. The balloon, after you rub it on your head, has a negative charge because it, like the comb, rips electrons away from your hair. And when you bring it over to the balloon, when you bring the balloon over to the wall, you see the same kind of temporary charge distribution that we saw with the paper. Now, let me just say before I flip the slide, the second image is different, but it illustrates the same concept. The only difference is that the wall here is now going to be on the right and the balloon is going to be on the left, but it's the same idea. The balloon here has this negative charge. The wall is neutral, but the electrons in all of the molecules in the wall get repelled by the negative charge on the balloon. And I didn't make this point before, but now we can say the reason why they attract is because now you have only positive charges from the protons that can't move in the wall next to the negative charges in the balloon. And so opposites attract. They attract and the balloon is able to stick to the wall. What's also probably important to emphasize, which we will get into tomorrow, is that the electrical force, obviously from this experiment, is way bigger than the gravitational force, because there still is a gravitational force acting down on the balloon. If you have a balloon in your hand and there's not helium in it, when you let it go, it goes down. But because this force of electricity directly to the right here, and also up from these protons that are above, because this force, the electrical forces are so much bigger, like many times bigger than the gravitational force, this thing is able to prevent itself from being in free fall and sticks to the wall. Now, since both of these examples were examples with charging objects, in this case the balloon, that were negatively charged, I want to go back to the board for a second and just very quickly go through the example of how you can induce this charge distribution in a neutral object when the charging object is positive.
Before we move on, I just want to make sure that we're taking the opportunity to just take a look at a neutral object being charged by a positive charging instrument. In a lot of these examples that we look at, we end up seeing a negative object coming in, but they also ask questions about a positive object coming in. And so I just want to make sure we're taking the opportunity to show that, fully understanding it, just really taking a look at both sides of the issue. So now, instead of having a negatively charged comb or something, let's say we had some sort of object that was positively charged. Essentially, the way that this would become positively charged is exactly the opposite of the way the comb became negatively charged. As I said, the comb usually becomes negatively charged when it's rubbed on hair because it rips away electrons from your hair. It is also possible, using a different type of material, to have this object being rubbed on that material, and instead of ripping electrons away from that material, it gets electrons ripped away from itself. And so that would mean that this object, this rod here, would be positively charged if it has its electrons removed. So here's the before picture. That positively charged rod is some distance away from this neutral object, and so it's not affecting it. But now, let's say, instead of having this be some distance away, we bring it over close to the sphere. So now we have this positively charged object all up in this sphere. It's very close, and now it's going to work its magic. Of course, we have to ask the question, well, what's going to happen? Well, as we said last time, we are not going to consider what the protons do. Why not? Because protons do not move in solids. So we just need to consider what the electrons do. And as we said, the electrons are going to be attracted now to this positive charge. And so they're going to bunch up as best they can on the left-hand side of the sphere. The protons, on the other hand, that were originally on the right side, get left behind. And so the right side ends up getting a net positive charge. That's ultimately the way this works. And again, we say that this thing experiences what we refer to as a temporary charge distribution, because effectively how this works is we have a negative net charge on the left side, a positive net charge on the right side. It's a temporary charge distribution. Notice this totally explains why it gets attracted, because now you have positive next to negative, and hello, positives attracts to negative, so they get attracted. That's the deal. Notice that's the same thing, actually, if we go back and talk about what this looked like for the negative charging instrument. As we saw with our piece of paper here, yeah, all the electrons moved away, the protons hung around, and now you have electrons in the comb being stuck next to the positive charges in the paper, and so they attract. You could especially notice this if you were paying attention to the comb video, because like if this was the comb, when it picked up the pieces of paper, you notice the individual strips were stuck to the comb long ways. That's because only one side of the paper was attracted to the negative charges on the comb. The other side was repelled. And so it actually does attract to the comb like this, where the one side is facing the comb and the other side is facing A. Now, take a second to pause this video here and write this down. When you hit play, we'll take a look at another note before we move on. For these neutral objects being charged problems, it's really important to remember the protons do nothing. The electrons are always going to be attracted to positive external charges and repelled by negative external charges. That's the deal. Take a second to pause this video here and write that down. And when you hit play, we'll move on.
We're in the final stretch here. Let's just go ahead and wrap this up. There's one more important point to make. Because so far, while we've talked about charging these objects, like charging a neutral object, for example, as we mentioned before, that charge distribution is only temporary. So the question is, how do you give a permanent charge by induction? First thing we need to say is that because there's no contact in induction, there is no charge transferred between the objects. You only get that temporary charge distribution. However, the object can be charged by induction if you connect the object being charged to ground. Now, since you guys have taken basic electricity for shop, I'm sure you remember what a ground is. A ground is either a place where you can send a bunch of excess electrons. That's usually how we use it in a circuit, because the circuit has a bunch of electrons flowing through it. And if you have too many flowing through a circuit, it could fry all your components. And so if there are extra, you want to be able to give them a place to go. That would be a ground. Or if an object has too much positive charge, it can actually get some electrons from the ground to balance it out. So a ground is either a place where electrons can go or where electrons can come from. So what I want to do is I want to show you a picture of how it works and then give you two big notes. So this is a moving image here, it'll show. So we have this negatively charged object being brought to this neutral sphere. As you can see, there's a temporary charge distribution. We get all those positives bunching up on the right, the negatives, or the positives on the left, the negatives on the right. Now a person brings in their finger and touches the sphere. You saw that little ground symbol, which you may recognize from basic electricity. And what happened is all the electrons went away from the sphere because they were all bunched up on that side. They did not like being all together. And so it's going to show that again. Notice once those electrons all bunch up on the right side, they are uncomfortable. They are all repelling each other. And if they are given a place to go, they'll go somewhere. And when the person touches their hand to it, they're all like, oh, nice, we can get out of here. And so they leave. Now, since there are more protons on the sphere than electrons, the sphere is positive. Now, this image has one thing about it that is remarkably wrong. And that's that they show the protons in the sphere moving, which they certainly cannot. This is okay. This is from a not a perfect website, but it's good enough. Protons don't move, but the electrons can. And when the thing is connected to ground, the electrons will leave because they are all repelling each other on that side. Now, because there are more protons, the thing is positively charged. And so now before we wrap this up, we have two quick notes. The first note is, when you charge an object by induction, the object gets the opposite charge as the charging object. Notice, I'm going to flip off this for a second, I'll come back. Notice this object was negatively charged. Once you connect this thing to ground and those excess electrons on the right-hand side go away, you have a positive charge on the sphere. So when you bring the negatively charged object over, the sphere ends up getting the opposite charge, positive, from the charging object. The last thing we'll say is that this is different from conduction because, as we saw yesterday, when you charge an object by conduction, it causes the object to have the same charge as the charging object. So to put it simply, induction gives you the opposite charge, conduction gives you the same charge. Before we wrap this up, I just want to see how that plays out in one problem very quickly, and that'll be it for today. This problem says here, negatively charged rod A is used to charge rod B by induction. Object C is then charged by direct contact with rod B. The charge on object C is neutral, positive, negative, or not able to be determined. I'd like you to pause this video now, take a second to think about it, come up with an answer, and then when you hit play, I'll discuss the answer. Did you pause it? I hope so. If not, pause and think about it. This is an important question. So they tell us here that this negatively charged rod A is used to charge rod B by induction. As we just said, when an object is charged by induction, it gets the opposite sign from the charging object. So since the charging object here is negative, rod B is going to get the opposite sign. So rod B is going to be positive. Now it says object C is charged by direct contact with rod B. That means object C is charged by conduction. And that means when object C is charged by conduction, it gets the same charge as the charging object, which would be positive. That makes the answer here choice 2. The main idea is that when object B, rod B, is charged by induction, it gets the opposite charge as the charging instrument. So because the charging instrument is negative, rod B is positive. Then when rod B charges rod C by conduction, object C gets the same charge as rod B, making it also positive. All right, guys, that is it for today's video. Remember, there is also a series of questions for you to answer about the concepts that were covered in this video. Please make sure you do not forget to go ahead and answer those. In the next video, I'm going to take some time to go over the answers to those questions, talk about any of the ones you might have had difficulty with before we move on to the next topic. All right, everybody, have a good one.